Part C.3, Exhaustive Search. In this part, we try to use another commonly used brute force method, exhaustive search. From this name, you can see we need to exhaust all the possibilities. That reflects the brute force method. But just another view of this brute force method. So let's look at the problem. Problem number 7. Traveling salesman problem, TSP. This is a very famous problem. Traveling salesman problem, TSP. Extremely hard problem. Extremely hard. Yeah. If you want to find an optimal solution, here, so if we want to talk about optimal solution, extremely hard. Nobody can do it. Nobody can do it. Yeah. But here, in our first try, we don't want to find an optimal solution. We just want to find one solution. How about that? Yeah. Is it good or not good at this point? Because it is our first try, right? So we just try to get a starting point. We just try to use the brute force method, exhaustive search, to get a starting point. All right, the problem, given N cities with known locations. Find a shortest tour. Tour among those cities. There are many different tours, but there is one that is the shortest. Shortest tour through all these cities that visit each city exactly once before returning to the city where it started. Yeah. So you can imagine. Yeah. Understand the problem. It is very easy. So what we know, what we need to do, but find an optimal solution. Find an optimal solution with acceptable performance is very hard. Acceptable performance, very hard. Because currently, all the methods solving this problem do not perform well. Very slow. Yeah. So that's the main problem. Okay? Yeah. All right. Yeah. Question. Can we exhaust all the tools that satisfy the requirement? Yeah. So the first thing, we try to exhaust all the tours. Yeah. Okay? Yeah? Because we can imagine, we can go through all the possible tours. Yeah. The first thing, we need to describe those tours. We need to describe. Okay? So let's do step by step to describe all the tours. Okay? Yeah, let's do it. Yeah. We need to calculate the distance between two cities first. Okay? Locations are known. How do we represent locations of the cities? We use coordinates, XY coordinates. Yeah. So let's use the standard way to represent locations. How to find a different distance between two cities with given coordinates. Okay, yeah. You should know the formula. Yeah. Here, I just write the formula here. Yeah. Based on the Pythagorean theorem. Yeah. Like that. So we use Dij to represent the distance between city I and city J. Okay. All right. To describe a city. Now let's take a closer look. To describe a city. What is the simplest way to represent a city? Representation, mathematical representation. We want to use the simplest way. Okay? When we represent a city, do we need to use its name? We don't need. Do we need to use its location? We don't need. Do we need to use its population? We don't need, right? Yeah. So the simplest representation, we do a lot of abstraction. We just use a number to represent it. We just use number I to represent city I. That's simple. Okay? It's number I to represent city I. That's simple. Okay? Yeah. All right. After we represent city, just use numbers. How to represent a tour. Next question. How to represent a tour in a simple way. Okay. Here, this tour should cover all the cities. Each city only cover once. Okay. Look at this way. Okay. City 1, then after that we go to city 4, city 2, city 5, and so on. Okay, city N, then back to city 1. Okay, yeah. Make sure no city repeated twice, except the first one. Yeah, because first one, finally we need to get back to the original city. Yeah. All right. The question is this representation good enough? Actually, we can simplify furthermore, right? All these errors, why we need these errors, right? So we don't need. So we can simplify to this way. Just a sequence of ordered numbers. Should be ordered because in a tour, the order of the cities, that is important. Yeah. So here you can see our new representation, this one, that corresponds a concept we learned before, permutation. In our discrete math, we learned the permutation. Right? Yeah. Now we need to use that concept, permutation concept, to describe a tour. Okay? And this representation is one-to-one correspondence. When you have a tour, you can get its corresponding permutation. When you have a permutation, you can get its corresponding tour. Okay? Yeah. So this kind of one-to-one correspondence is very useful to describe a tour. Yeah. All right. Next. So we want to look at the number of permutations. How many permutations do we have in n numbers? Yeah. So you learn in your discrete math, right? Yeah. If you remember the answer is n factorial. N factorial, permutation numbers. Okay. That means our number of tours, we have the same number, n factorial. Okay. This is a big number. Why the traveling salesman problem is so hard to solve? Because the number of tours is a huge number. That's the main reason it is so hard to solve. Efficiently. Here, I want to add that word efficiently. If not efficiently, then anyone can solve. Okay? But efficiently, extremely hard. Yeah. All right, so next, let's try to represent a general tool using symbols, using good symbols to represent. Yeah. Here, because we just want to represent a permutation. Yeah. Here I use pi, it's not a, circle, that pi, that coefficient. Yeah. This is a symbol pi, okay, permutation. Yeah. Pi equals I1, I2, In permutation. Yeah. Very general representation of a permutation. If we have that, then we can represent total distance for a general tool for this representation. Yeah. Our distance expression is, we use the summation notation, sigma, big sigma, summation notation. I think in your discrete math, you learn it. Okay, you should know it. Yeah. So here, each d, the distance between city ik to ik plus 1. Here you can see our notation pretty complicated. Subscript of subscript. Yeah. So d has a subscript, and its subscript has another subscript. So that's why, it is a little complicated. All right. And because at the end, you need to get back to the original city, so we make In plus 1 equal to I1. Yeah. After city n, the nth city, the next one, back to the first one. Yeah. That's the meaning. Yeah. So with that, you can represent the total distance of one tour in this way. Okay. After that, then we can look at the total cost. Yeah. Conclusion. Yeah. Given a tour, so we can easily find its total distance using the 2-point distance formula. In our previous slide, we have that 2-point distance formula. So for each term in the summation, we apply that 2-point distance formula so we can calculate the total distance. Okay. All right. So we can find answer for each tour, the number, the total distance. Yeah. Objective of our next step. Estimate the efficiency of the exhaustive search for the TSP problem. If we want to find the shortest tour, what is the efficiency for that exhaustive search algorithm? In our next slide, we want to see it. Yeah. All right. To solve that problem, we need some tool to help us. Yeah. All right. First, let's represent, because here we applied exhaustive search. Let's exhaust all the tours in our symbols. Pi 1, pi 2, ... pi r, that r equals N Factorial. So we exhaust all the tours. Okay, yeah. And because given a tour, we can calculate its total distance. So we use d pi 1, d pi 2, d pi r to represent the total distance for all the tours. Yeah. Among them, we can get optimal solution. Yeah. Or we can get a shortest tour by calculating the minimum of those numbers. And we have that solution in r minus 1 comparisons. So we did that before. Yeah. Now at the end, efficiency. Efficiency is at this step. In order to calculate all these numbers, that is very expensive. That is very expensive. That's the dominant term. To find a minimum, it is less expensive than calculate all the distance. So let's look at how much cost do we need to calculate all the distances. Okay? N times N factorial. Yeah. Because for each distance, you need to calculate that 2-point distance N times, right? Adding together. N times, then adding together. So that operation number is N. But you have total N factorial number of tours. So that is the total number of operations, N times N factorial. Yeah. All right. So next, to estimate N factorial, we need to use the Stirling's formula. We used that before. So remember, when we calculate the, N factorial limit, remember that growth function, when we compare growth functions. So we did that before. So we need to use the Stirling formula another time. Okay? So we use this version. Yeah. Lower bound and upper bound of N factorial. Okay. So with this formula, then we can estimate this asymptotic notation. We can use big theta. So here we can do better estimate than big O. Yeah, because big O is pretty rough, right? It is pretty rough. But now we use big theta. Okay? The big theta, we have lower bound and upper bound. Okay? Yeah. And because the constant part is not important, so we only look at the variable part, and its exponent, n plus 3/2. So because we have times n, so we have 1, right? And 1/2, square root of n, we have 1/2. Yeah. But at the bottom, e to the nth power, we need to include it. Yeah. So that's why the final result, if we use the exhaustive search, that is this expression. So we use our asymptotic notation, we can get a nice representation for the efficiency of this algorithm. All right, so we complete part C.3.